The story of the universe is one of explosions and expansion of stars and galaxies born from clouds of dust and gas. Yet for hundreds of millions of years after the Big Bang, the cosmos was shrouded in darkness. Photons, the particles of light, were lost in a sea of hydrogen, unable to travel far before being absorbed. This period, known as the Dark Ages, lasted from a few 100,000 years after the Big Bang until the universe was transformed by an event called reionization. It's a pivotal but hidden chapter in cosmic history. We can see the universe today with its galaxies filled with stars and glowing nebulae, because reionization made the cosmos transparent. Before that, the universe was opaque. Stars couldn't form, galaxies couldn't assemble, and there was no light as we understand it. The transition to an enlightened cosmos began when the first luminous objects ignited in the darkness. These early stars formed from collapsing clouds of hydrogen and helium, the two lightest elements forged in the fires of the Big Bang. As these clouds collapsed, they heated up dramatically and began to glow. When they reached 10,000 degrees Celsius, nuclear fusion ignited. Hydrogen atoms fused into helium, releasing even more energy, which made the stars shine brighter. With each passing million years, more stars ignited, forming the first galaxies. These early galaxies didn't resemble the grand spirals and ellipticals we see today. They were smaller, irregular, and violently chaotic places where star formation was rampant. Each star was many times larger and more massive than our Sun. Within their blazing cores, they fused hydrogen into helium at a furious pace. And as they did so, they released powerful bursts of ultraviolet radiation. This radiation carried enough energy to break apart hydrogen atoms, stripping them of their electrons. The freed electrons were drawn to the intense gravity of nearby stars and galaxies, creating vast clouds of ionized hydrogen around them. And that's when something extraordinary happened. As the clouds of ionized hydrogen grew, they began to glow. This wasn't just because of the radiation from nearby stars. It was also a direct result of the electrons recombining with protons to form neutral hydrogen atoms again. When this happened, the electrons released energy in the form of ultraviolet photons. These photons were less energetic than those bombarding the hydrogen from space, but they were still powerful enough to ionize more hydrogen, keeping the cycle going. So we went from darkness to light, as radiation from the first stars ionized the hydrogen, making the universe transparent. This process didn't happen overnight. It took hundreds of millions of years for the radiation from the first stars to completely break apart the hydrogen. But eventually, the universe became transparent. The galaxies could assemble from the remaining neutral hydrogen. And as the cosmos continued to expand and cool, things started to settle down. Stars formed in giant gas clouds, planets coalesced around those stars, and life as we know it could begin. But the details of reionization remain shrouded in mystery. Astronomers know it happened, but exactly how and why are still unknown. For example, while we know the first stars played a major role in reionization, we don't know what they looked like, how big they were, or how they formed. We also do not know what happened to the electrons that filled the universe once hydrogen was broken apart. And finally, we don't know exactly when reionization ended. To solve these mysteries, astronomers are turning to some of the most powerful telescopes in the world, including the James Webb Space Telescope. By studying the ultraviolet light from distant galaxies, Webb will help astronomers better understand the nature of the first stars and their role in reionization. It will also allow scientists to measure the distribution of ionized hydrogen in the early universe, providing clues about when and how the cosmos became transparent. Webb has already captured some amazing images of the early universe, including one of the most detailed infrared images of the cosmos ever taken, known as the Cosmic Evolution Early Release Science Study. This image is just a small slice of the sky, yet it contains thousands of galaxies, each harboring hundreds of billions of stars. Many of these galaxies are so distant that their light has been stretched to infrared wavelengths, allowing Webb to see back in time nearly 13 billion years. Once Webb continues to explore the universe, it will shed more light on the mysterious process that turned our universe from dark to light.
This is a NASA science video.
When you think of empty space, you probably imagine a vacuum, a perfect void where nothing exists. But empty space can actually be a pretty relative term. Take the vast expanses between galaxies, for example. To the average person looking through a telescope, these areas might appear completely empty. But to astronomers, they're anything but. Those dark patches between galaxies are home to huge clouds of gas, dust, and even plasma, all stretching across unimaginable distances. And it turns out, these intergalactic voids play a critical role in understanding the universe as a whole. To really appreciate just how much stuff is out there, consider this. Our own galaxy, the Milky Way, contains around 100 billion stars. But if you were to take all the space between those stars and spread it out evenly throughout the entire universe, you would have only a fraction of an atom's width of empty space. The rest would be filled with matter. So while space between galaxies might look empty, it's really just a different kind of crowded. In fact, one of the most exciting areas of astronomy today is focused on understanding the nature of this stuff, what it's made of, how it got there, and how it moves around. Astronomers call this stuff the intergalactic medium, or IG. And despite making up a whopping 10% of the entire universe, we've actually only studied a tiny sliver of it. And now scientists have used data from the Era of Reionization telescope to create the first ever map showing how hot gas is distributed throughout 1.6 billion galaxies. What they found is both familiar and strange. Around 50 million light-years away from Earth lies the Perseus supercluster, a massive group of galaxies that includes the Andromeda Galaxy, M31. The galaxies within this cluster are so close together that they collectively form one giant, swirling mass of gas and plasma. But as you move further away from the cluster, the amount of hot gas between galaxies should decrease. And that's exactly what the map shows. The gas becomes more sparse, gradually fading into the depths of space. But here's where things get weird. When researchers compared their map with other surveys showing the distribution of galaxies, they found something unexpected. The hot gas wasn't smoothly distributed throughout the voids between galaxies. Instead, it was clumped and tangled in ways that closely matched the distribution of galaxies. And that's not surprising. Galaxies have a gravitational pull that extends far beyond their visible boundaries. And as the universe evolved, these gravitational wells would have pulled in surrounding gas, creating these dense, hot clumps. But there's another interesting feature. The map also shows that the hot gas isn't evenly spread out within the clumps themselves. Instead, it forms long, thin fingers that point away from the center of the galaxy like the spokes of a wheel. And that's because as these galactic gravitational wells pulled in surrounding gas, they also created shock waves that extended outward for hundreds of thousands of light years. These shock waves compressed the gas into thin sheets that aligned along the spokes of the galaxy-esque gravitational wheel. Understanding how this gas is distributed will help astronomers piece together the history of galaxy formation and evolution. But it also has implications for our understanding of the universe as a whole. That's because this hot gas isn't just some leftover material. It plays an active role in the life cycle of galaxies. As gas cools within a galaxy, it can form clouds that serve as the building blocks of new stars. So mapping its distribution is like finding the raw material that makes galaxies grow. It's early days, but this new map is already providing insights into how galaxies assemble over time. By shedding light on the stuff between galaxies, astronomers are finally seeing the universe in a new way. They're realizing that space is not empty, but filled with a complex, dynamic web of gas and plasma that plays a critical role in the evolution of galaxies and the universe as a whole. So the next time you look up at the night sky and see the vast emptiness of space, remember that what you're really seeing is a tangle of hot, glowing gas that stretches as far as the eye can see. Scientists have created the first ever map showing how hot gas is distributed throughout 1.6 billion galaxies. The end of the universe's dark ages wasn't a bang. It was a dawn, not a sudden event, but the gradual brightening of a previously invisible cosmos. And that light came from the first luminous objects in the universe, the very first galaxies and the strange stars that lit up the darkness. They are the stuff of cosmic legend, blazing giants unlike any star that shines today. These objects were not only the universe's first lights, but also the first ionizing radiation, high-energy photons that ripped apart the pervasive hydrogen fog, transforming the universe forever. But to understand this pivotal era, known as the Era of Reionization, we need to peer deep into the past and explore the dawn of starlight itself. In the beginning, the universe was dark, not in the sense of empty and featureless, but rather opaque and featureless. Everywhere, a thick fog of neutral hydrogen obscured the universe. Visible light couldn't penetrate it, leaving the cosmos shrouded in darkness. And though there was plenty of light present, specifically ultraviolet radiation streaming from the afterglow of the Big Bang, it was trapped inside the fog, unable to reach us. For hundreds of millions of years, the universe was stuck in this state, cut off from its own light. Then something changed. The first luminous objects ignited, the first galaxies and the stars within them. As these objects shone, they released ultraviolet radiation. And when that radiation struck hydrogen atoms, it ripped them apart, stripping away electrons and creating a sea of free electrons and protons. This is a process called ionization. So the universe was gradually carved from darkness into transparency by these early stars. They opened up the fabric of space, allowing light to travel freely for the first time. And once light was no longer trapped, the universe as we know it was born. The first light sources were nothing like our sun. Called population 3 stars, these colossal suns were vastly different from their descendants. Unlike stars today, they were born in a universe devoid of heavy elements. No carbon, no oxygen, no iron. Only a thin haze of trace elements remained from the Big Bang, mostly hydrogen and helium. Since there were no heavy elements to help the gas cool and clump together, the only stars that could form were massive. We don't know exactly how massive, but simulations suggest they may have reached 1,000 times the mass of the Sun. These enormous stars burned brightly, blazing across the night sky. Some simulations suggest they were up to 10 trillion times more luminous than the Sun, but their colossal size came at a cost. These stars lived fast and died young, whereas the Sun will live for 10 billion years. Population 3 stars likely lived for mere millions of years before exploding as supernova. In a universe without heavy elements, there was nothing to recycle the gas. Once they exploded, their ultraviolet radiation tore apart even more hydrogen. Atoms smattered across the cosmos, slowly carving out clear bubbles in the neutral hydrogen fog. Each bubble represented a region of space, ionized by one of these first stars. These stars were also cosmic alchemists. Inside their searing depths, hydrogen fused into helium, forging the universe's first heavier elements: carbon, oxygen, neon, silicon. And when they exploded as supernova, those elements were scattered into space. These newly forged elements played a crucial role. They allowed subsequent generations of stars to form in these same regions. That's because, as gas began to cool and condense into new stars, these elements helped it clump together more efficiently. And this marked the birth of a new class of stars, the second generation of stars called population 2 stars. These were smaller and longer lived, some of which still shine in the universe today. Some astronomers even believe that the faintest dwarf galaxies around the Milky Way are these ancient holdovers, relics of the early universe. Meanwhile, the first stars were seeding the universe with another phenomenon: black holes. Some population 3 stars, especially the most massive, didn't explode as supernova. Instead, they collapsed under their own gravity, imploding into infinitely dense points, black holes. If these initial black holes merged or fed on surrounding gas, they could have grown quickly, reaching thousands or even millions of times the mass of the Sun. Today, we see similarly massive black holes at the center of almost every galaxy, including our own. And many scientists believe they started this way, with seeds planted during the Era of Reionization. But the exact nature of these early black holes remains a mystery. How did they get so big so fast? Did they start from population 3 stars? Or did they form directly from collapsing gas clouds without ever igniting stars at all? Solving this puzzle will require looking deeper into the past, probing the very roots of the first galaxies. These galaxies were also nothing like those we see today. But in contrast to the grand spirals and ellipticals of today, the universe's first galaxies were tiny dwarfs, likely only 1,000th the size of the Milky Way. And yet they played a monumental role. The Era of Reionization didn't just mark the beginning of starlight, it also marked the beginning of galaxy formation. Stars formed within the densest regions of dark matter, where gravity was strong enough to pull together huge clouds of hydrogen. Those clouds became the first galaxies, or more accurately, proto-galaxies. Within them, the first stars ignited blazing giants unlike any that exist today. Together, they acted as reionization engines, bathing the universe in radiation and carving it from darkness into transparency. As time went on, stars exploded, seeding the surrounding gas with heavier elements. Second-generation stars formed, and the cycle continued. Over hundreds of millions of years, these early galaxies grew, assembling more stars and gas. But despite their small size, it's thought they were major contributors to reionization. Yet for all their importance, direct observation of these galaxies remains elusive. The further back in time we look, the further away a galaxy is, and the more distant it appears. And the more distant it is, the more redshifted its light becomes. Redshift happens as space stretches over billions of years. It causes light waves to stretch and shift towards the red end of the spectrum, making the galaxy appear more and more red. Telescopes can see through this redshift, but there is a limit. Eventually, the light from these galaxies becomes so stretched that it falls outside the range of visible light. Most telescopes can't detect anything beyond that. That's why astronomers rely on powerful telescopes like Hubble and the James Webb Space Telescope, JWST. Hubble has peered back through time and captured images of some of the earliest galaxies ever seen. Meanwhile, JWST is pushing the limits even further, detecting galaxies less than 500 million years after the Big Bang. It's helping astronomers better understand the epoch of reionization by observing the light from these distant galaxies. By studying their properties, scientists hope to learn about the galaxy's shapes, sizes, and compositions, and by extension, about the nature of the first stars that formed within them. One of the things astronomers are eager to learn is whether these early galaxies formed from the bottom up. That is, did they start small and grow, or did they assemble rapidly in one fell swoop? The evidence so far seems to favor the gradual approach. Observations of the universe's first luminous objects are consistent with the idea that they formed gradually from small clumps of dark matter. Another piece of the puzzle comes from simulations. By recreating the conditions of the early universe on supercomputers, scientists can simulate how stars and galaxies formed and evolved. These simulations are essential because they allow astronomers to compare predictions with observations and test various models. Recent simulations have revealed some surprises, such as the chaotic and turbulent nature of the early cosmos. Early gas clouds were not static, but roiled with motion. Affected by the gravitational pull of nearby dark matter and the energy from the Big Bang's afterglow. This environment led to a burst of rapid star formation, followed by long periods of relative calm. These dynamic cycles may explain why the early universe saw a brief period of intense galaxy formation, followed by slower growth. It's also possible that not all early galaxies formed in this way. Some may have assembled more rapidly, growing quickly from massive gas clouds. Others may have formed from mergers between smaller galaxies. As astronomers analyze data from telescopes like Hubble and JWST, they'll be able to refine these models and better understand how the universe's first galaxies evolved. What's more, these simulations have provided a window into the lives of the first stars, showing how they shone, how they exploded, and how they dispersed heavy elements into the universe. They've revealed the dramatic events that shaped the early cosmos and allowed the universe to become visible. Yet despite all the progress made, much about the era of reionization remains a mystery. What were the exact properties of the first stars and galaxies? How did they contribute to the enrichment of heavy elements? How did black holes seed the growth of galaxies? And how did the universe transition from darkness into transparency? These questions continue to drive research, pushing astronomers to observe further, simulate deeper, and theorize anew. For the quest to understand the era of reionization is more than a journey into the past. It's a journey to the origins of the universe as we know it. It's the story of how light transformed darkness into dawn and revealed the wonders of the cosmos. It's the epic tale of the first luminous objects, the first stars, and the first galaxies, the cosmic pioneers that illuminated the darkness and set the stage for the universe as we know it. When exactly reionization occurred, the era of reionization, one of the most important transitions in the universe's history. But despite decades of study, its timing duration, and the exact sources of ionizing radiation remain some of the most hotly debated topics in modern cosmology, a window of uncertainty. We know reionization occurred within the first billion years after the Big Bang, but pinpointing the exact window is surprisingly difficult. Why? Because the evidence we rely on is indirect. Unlike the cosmic microwave background, which gives us a clear snapshot of the universe 380,000 years after the Big Bang, reionization leaves no single frozen image. Instead, it leaves behind subtle signatures imprinted on the light of distant objects and in the large-scale structure of the universe. The challenge is piecing together these signatures into a coherent timeline. Quasar clues. One of the most important tools comes from quasars, the brilliant beacons of supermassive black holes at the centers of early galaxies. When we look at quasars that existed around 12 to 13 billion years ago, their light has traveled across vast distances, passing through the intergalactic medium IgM. Neutral hydrogen absorbs specific wavelengths of this light, leaving behind a characteristic imprint known as the Gunn-Peterson trough. By studying these absorption features, astronomers can estimate how much of the universe was still neutral at the time the quasar S light traveled through it. What they found is striking. At redshifts around Z approximately equals 6, about 1 billion years after the Big Bang, the universe appears largely ionized. At higher redshifts around Z approximately equals 7 or 8, 600 to 700 million years after the Big Bang. Evidence suggests there was still a significant fraction of neutral hydrogen. This implies reionization was not instantaneous, it stretched over several hundred million years. Another important clue comes from studying the abundance of reionized gas on the largest scales. By measuring the distribution of quasars at different ionization states, astronomers can piece together when and how the universe became transparent. Some studies indicate that the transition from neutral to ionized was rapid, possibly taking just a few hundred million years. Others suggest a slower process spanning up to a billion years. CMB polarization. Another window into reionization comes from the polarization of the cosmic microwave background, CMB. As the universe reionized, free electrons once again filled space. These electrons could scatter CMB photons, leaving a measurable effect on the polarization of the microwave background. By analyzing this polarization, satellites such as WMAP and Planck have provided estimates for when reionization started. A patchy universe. One of the most fascinating aspects of reionization is that it was likely patchy, not uniform. Different regions of the universe ionized at different times depending on when and where galaxies formed. Dense regions with many early galaxies may have reionized quickly. Vast voids, with little star formation, may have remained neutral longer. This patchiness complicates our measurements. Depending on which line of sight we observe, the universe may appear more or less ionized at the same cosmic time. Who did the work? Another unresolved mystery is identifying the main contributors of ionizing radiation. Candidates include population 3 stars, massive, short-lived, and incredibly bright. They produced copious ionizing photons, but did they live long enough and in large enough numbers to reionize the universe on their own? Normal galaxies. Later generations of stars in early galaxies may have provided the bulk of the radiation, especially if a large fraction of their ionizing light escaped into intergalactic space. Quasars, while powerful, they appear too rare at early times to account for most of the ionization. The current consensus leans toward galaxies being the dominant drivers, but population 3 stars and quasars may have played key supporting roles. The 21-centimeter frontier. Perhaps the most promising frontier for unlocking the timeline of reionization lies in the 21-centimeter line of neutral hydrogen. Imagine as neutral hydrogen atoms flip the spin of their electrons. They emit or absorb radiation at a wavelength of 21 centimeters. By observing this signal across cosmic time, astronomers hope to directly map the progress of reionization. Projects like LAFER, Hera, and the upcoming Square Kilometre Array SKA are attempting to detect this faint signal from the cosmic dawn. If successful, these maps would provide the first direct, large-scale view of how and when reionization unfolded. The puzzle still stands. Despite all these clues, key questions remain unanswered. Exactly how long did reionization take? Was it dominated by countless small galaxies, or by a few massive luminous ones? Did population 3 stars play a starring role, or were they merely the opening act? What we do know is that by 1 billion years after the Big Bang, the process was complete. The hydrogen fog had lifted. The universe was transparent. But this raises another question. What does reionization mean for us? Why does this ancient process, billions of light years away, matter to life on Earth? Reionization and the epoch of darkness. To understand why reionization matters, let's rewind time further. Let's go back to an even earlier epoch, known as the Epoch of Darkness, around 1 million years after the Big Bang. The universe was a sea of particles. The photons created during the Big Bang couldn't travel far. They were trapped, scattered by free electrons, preventing them from spreading. The universe was opaque. Light couldn't reach distant regions, keeping the cosmos shrouded in darkness. This period ended when the universe cooled enough for protons and electrons to combine, forming neutral hydrogen. Photons were finally set free. They raced across the universe, filling it with light. The universe became transparent. This allowed the cosmic microwave background radiation we see today to form. Now let's fast forward to the epoch of reionization. By this time, the universe was filled with the first galaxies, blazing with starlight. But something happened that scientists are still working to understand. The universe went from being mostly transparent to mostly opaque again. This period lasted from about 150 million to 1 billion years after the Big Bang. During this time, the universe was once again filled with free electrons. Once again, photons couldn't travel freely, preventing the universe from becoming transparent. But here's the twist. Unlike the epoch of darkness, where the opacity resulted from a plasma of free electrons and protons, the opacity during reionization was due to neutral hydrogen gas. This means that during the epoch of reionization, the universe was filled with an intergalactic medium consisting of clouds of hydrogen gas. Understanding how this happened and what followed is key to understanding how galaxies evolved. Why does it matter? You might be wondering why understanding what happened during this era matters to us today. After all, it happened billions of years ago. Well, the answer lies in the details of what happened during reionization. During this era, we know that the intergalactic medium was full of huge clouds of hydrogen gas. But what we don't know is how exactly this gas was distributed. If the gas was evenly distributed throughout the universe, it would have been easier for ultraviolet radiation from the first stars and galaxies to ionize it. However, if the gas was clumped together into enormous clouds, it would have been harder to ionize. This is important because how the gas was distributed during reionization tells us how matter was distributed throughout the early universe. And understanding how matter was distributed helps us understand how galaxies formed. That's because matter, including the hydrogen gas that was present during reionization, doesn't just randomly clump together. Gravity plays a major role. The way gravity causes matter to clump together today is the same way it caused gas to clump together during reionization. So by understanding how the gas was distributed during reionization, we gain insight into how gravity worked in the early universe. It also helps us better understand how galaxies evolved. We think that during reionization, most of the hydrogen gas in the intergalactic medium came from the early galaxies. As the first galaxies formed and began creating stars, they also expelled gas. This gas eventually filled the space between galaxies, creating the intergalactic medium. But we don't know how this happened. If the gas was evenly distributed, it means that ultraviolet radiation from the first stars and galaxies was able to ionize it relatively easily. This suggests that the first galaxies were quite massive, producing lots of ultraviolet radiation. On the other hand, if the gas was clumped together, it means that the intergalactic medium was hard to ionize. This suggests that smaller galaxies were able to produce enough ultraviolet radiation to ionize the gas near them, but not enough to ionize gas further away. Understanding the details of reionization will help us better understand the role that galaxies played in shaping the universe as we know it. Conclusion. In conclusion, reionization is a pivotal chapter in the universe's history. Though shrouded in mystery, its importance in shaping the cosmos as we know it cannot be overstated. The journey to unraveling this cosmic enigma has led us through the study of quasars and the polarization of the cosmic microwave background. Each clue brings us closer to understanding the timeline of this epoch, yet questions persist. When did it begin and end? Which celestial bodies played the starring roles? And what does this ancient process signify for us today? As we continue to probe the depths of space, we inch closer to solving this puzzle. With each new discovery, we refine our understanding of the universe's evolution, reminding us that even in the vastness of the cosmos, every detail matters. What are your thoughts on the mysteries of reionization? Do you find it fascinating or perplexing? Share your thoughts below. The universe's dark ages are over, and there was a period of history so remote and dramatic that you've probably never heard of it before. It's called the Era of Reionization. And though it sounds technical, imagine what it was like. It was the first era of light in the entire cosmos. Imagine a universe filled with great voids of impenetrable darkness, broken only by the sudden flaring of new stars and galaxies, each a blazing island of light pushing back the encroaching dark. That was the Era of Reionization, and it was a time unlike any other in the history of the universe. And it all started with the birth of the first stars. It's the first stars and the beginning of light. The Era of Reionization took place about 250 million years before the Big Bang. The universe at that point was mostly empty. The first stars ignited in the vast emptiness and became the nuclei around which galaxies would eventually form. These stars were gigantic, several hundred times the mass of the Sun. They were also extremely hot and luminous, and as they aged, they steadily produced heavier elements in their cores. One day, these massive stars exploded as supernova, leaving behind clouds of enriched gas and dust, seeding the universe with the building blocks of planets, rocks, and living things. This was a momentous event. Before this, the universe was as simple as it was empty. It contained only hydrogen and helium. After this, the universe became rich in elements such as carbon, nitrogen, oxygen, silicon, and iron, the stuff that makes up the Earth and you and me. With this enrichment came the potential for complexity, setting the stage for the evolution of stars, galaxies, and eventually, life itself. This was the start of the Era of Reionization, a new kind of universe. Now, here's where things get interesting. The first stars didn't just bring light into the universe. They also brought change. As they shone, they released enormous amounts of energy in the form of ultraviolet radiation. This radiation had a profound effect on the neutral hydrogen gas that permeated the universe. The radiation stripped electrons away from the hydrogen atoms, turning them into ions. This ionization transformed the universe, making it less dense, more transparent, and much hotter. The result was a fundamental shift in how matter and energy interacted. And this change was so profound that astronomers refer to it as the second Big Bang. Not quite. The first Big Bang refers to the initial expansion of the universe. This was something totally different, a change within the universe. It changed how matter behaved, how light propagated, and even how structures formed. And one of the most important things it did was that it cleared the way for galaxies to take shape. The cosmic web. You see, in the period before reionization, the universe was like fog. Ultraviolet light couldn't travel very far. It was constantly absorbed by neutral hydrogen, which acted like a thick blanket, blocking the view of anything lying beyond. This meant that the first stars and galaxies could unreally be seen except by those who were close enough to them. Once reionization occurred, however, the universe became much more transparent. Light could now travel hundreds of millions of times further before being absorbed. This newfound transparency had several consequences. First, it allowed the light from the first galaxies to reach us, enabling us to peer back in time and witness the dawn of cosmic structure. Second, it made the universe more three-dimensional. Before reionization, most of the action was confined to thin sheets and filaments. Once reionization occurred, structures like the cosmic web began to emerge. The material in space was drawn together by gravity, creating a vast network of galaxy clusters, superclusters, and immense voids. It was during this time that the large-scale structure of the universe began to take shape. It's the Milky Way and other galaxies. Now let's zoom in a little and focus on our home, the Milky Way. The galaxy we live in didn't just suddenly pop into existence during reionization. Like most things in the universe, it evolved gradually over billions of years. But the process of reionization did play a crucial role in its formation. Our galaxy, like all others, began as a small, dense clump of gas and dust. However, this clump wasn't big enough to sustain star formation until reionization. The ultraviolet radiation from the first stars ionized the surrounding gas, heating it and speeding up the process of gravitational collapse. This created a positive feedback loop. As the galaxy grew, its gravitational pull increased, drawing in more gas and accelerating its own growth. In essence, reionization provided the kick our galaxy needed to start forming stars. It was like a cosmic nudge that set the Milky Way on its path to becoming the home of trillions of stars and planets. Without reionization, it's likely that the Milky Way would have formed much later, if at all, at the end of an era. So when did the era of reionization end? Astronomers generally agree that it lasted until about 1 billion years after the Big Bang. By then, the universe was filled with stars and galaxies, and the process of ionization had reached a steady state. It's like when a forest reaches its climax. No major changes occur anymore. The ecosystem is stable and balanced. But it's important to remember that the process of reionization wasn't uniform. Different parts of the universe ionized at different rates. In some places, reionization continued later, perhaps even until 100 billion years after the Big Bang. The legacy of reionization. Today we find ourselves living in the aftermath of reionization. The universe we inhabit is shaped by the processes that occurred during that remarkable era. The stars and galaxies that emerged during reionization are the progenitors of the structures we see today. Even the Earth and the Sun are, in a sense, fossils of that era, with their compositions reflecting the conditions that prevailed back then. Moreover, the era of reionization was a transformative period in the history of the universe. It marked the transition from a simple, homogeneous universe to one filled with stars, galaxies, and complex structures. It also set the stage for the emergence of life. The elements forged in the hearts of the first stars, the building blocks of life, were scattered across the universe during reionization. These elements, carried by dust and gas, eventually formed the planets and biomolecules necessary for life as we know it. In short, reionization was not just a chapter in the history of the universe. It was a foundation upon which everything we know has been built. As we continue to explore the cosmos, we are constantly reminded of this. From the structure of galaxies to the composition of stars, the imprint of reionization is everywhere. Understanding this era is not just about unraveling the past. It's about appreciating the interconnectedness of everything in the universe. We are not just observers of the cosmos. We are participants in a grand story that began with the first stars and continues to unfold today. We are the legacy of reionization. The fact that you're watching this video right now is, in a way, a testament to the incredible events of reionization. The fact that you're alive right now is, in a way, a testament to the incredible events of reionization. It was a time of immense change, a cosmic revolution that transformed the universe and set the stage for everything we know. As we continue to explore the cosmos, we carry the story of reionization with us. Every star we observe, every galaxy we chart, is a reminder of the epic events that shaped our universe. The era of reionization may be long over, but its legacy lives on in the stars that shine above us and in the very atoms that make up our world. We are truly the children of the cosmos, born in the light of the first stars and sustained by the energy of reionization. As we look up at the night sky, we should not just see stars, but a story, the story of our origins, a story that began with the birth of the first stars and continues to unfold today. A story that is both epic and deeply personal, a story that is, in the end, our story. In the grand narrative of the universe, there's a period so shrouded in mystery that it's earned the title of Cosmic Dark Ages. It's the era after the Big Bang. Before the formation of stars and galaxies, a time known as the Dark Ages, imagine a universe so alien that even light couldn't travel freely. Picture a vast dark canvas dotted with distant galaxies, each a potential enigma. This isn't science fiction. It's our universe as it existed over 13 billion years ago. But the story doesn't end there. As we gaze deeper into space, we encounter the cosmic dawn, a period when the first stars flickered to life. It marked a pivotal moment, a transition from darkness to light, order to chaos, an era that set the stage for everything we know today. But here's the intrigue. The light from these ancient stars didn't travel to us unhindered. It encountered a universe still recovering from the primordial plasma state, a dense sea of particles. This light was absorbed, scattered, and distorted by a haze of neutral hydrogen atoms blanketing the cosmos. The universe was effectively opaque. It took hundreds of millions of years for these early galaxies to punch through this fog, ionizing the neutral hydrogen and making the universe transparent. We call this process reionization. Yet the more we learn about the universe, the more it seems we understand less. What we think we know about reionization, based on the best data we currently have, is that it occurred in two phases. The first phase started soon after the Big Bang, when the universe was around 400,000 years old. During this time, the universe cooled sufficiently for protons and electrons to combine, forming neutral hydrogen. Then came the second phase, the period of cosmic dusk. This phase began when the first stars exploded as supernova, releasing ultraviolet radiation that ionized the neutral hydrogen. What's fascinating is that both phases of reionization remain poorly understood, despite being crucial moments in cosmic evolution. This lack of understanding isn't due to a lack of effort. Since the 1960s, astronomers have been tirelessly working to decode the universe's history, piecing together this narrative from the faintest whispers of light that have reached us. Now, standing on the shoulders of these giants, we are about to enter a new era of discovery. Imagine if you had a friend who could tell you about the days leading up to a surprise party, but all their descriptions were secondhand. That's essentially the situation we're in regarding the period of cosmic dusk. All our information comes from indirect observations, like the fact that we can't see gamma rays from this era. Why? Because the universe was too filled with neutral hydrogen, which absorbed those rays. However, we do see a surge in gamma rays shortly after the first stars formed, indicating that something big happened. Our goal is to find out what. And now we have the tools to do this. Let's delve into the secrets of the cosmic dawn and explore the incredible methods astronomers are employing to shed light on this era. One of the most powerful tools in our arsenal is a technique called gravitational lensing. Gravitational lensing allows us to magnify and distort the images of distant objects, making them easier to observe. It works because massive objects like galaxies warp the fabric of spacetime around them. This warping acts like a lens, bending and magnifying the light from objects located behind them. With this technique, we can peer deep into space as if we had eyes that spanned light years. Another powerful tool is spectroscopy, which allows us to analyze the composition of distant objects by splitting light into its various wavelengths. Each element has a unique spectral signature, like a barcode. So when we observe a spectrum, we can identify which elements are present. This helps us understand the chemical makeup of stars, galaxies, and other objects in the universe. Additionally, we can determine the speed of these objects by measuring the Doppler shift of their light. If an object is moving towards us, its light will be blue shifted. If it's moving away, its light will be red shifted. Now let's talk about the cosmic dawn, the era when the universe went from opaque to transparent. During this time, the first stars ignited, bathing the cosmos in ultraviolet radiation. This radiation collided with neutral hydrogen, stripping away the electrons and turning the universe transparent. Scientists believe that the majority of the hydrogen was ionized within a few 100 million years after the Big Bang. But how exactly did they figure this out? Well, let's dive into a method called the Gunn-Peterson test. This method involves examining the spectra of distant quasars, which are incredibly luminous and active galactic nuclei found in the early universe. They serve as beacons, allowing us to study the intergalactic medium, the matter between galaxies. When the light from quasars passes through clouds of neutral hydrogen, they cause a specific pattern of absorption. By studying these absorption lines, scientists can determine the amount of neutral hydrogen present in the universe. The deeper the line of absorption, the more neutral hydrogen there is. The Gunn-Peterson test revealed a dramatic drop in the number of neutral hydrogen atoms at a redshift of around. This finding suggests that the universe had largely been reionized by this point, marking a significant leap in our understanding of the early universe. Now let's turn our attention to another fascinating aspect of the cosmic dawn, the epoch of reionization. This period witnessed the formation of the first galaxies and stars, along with the subsequent ionization of hydrogen. It's a pivotal era in the universe's history. shaping the large-scale structure of galaxies and influencing the distribution of matter throughout the cosmos. During the epoch of reionization, the universe was filled with a fog of neutral hydrogen. This fog hindered the ability of light to travel freely, limiting our view of the universe. But thanks to advancements in technology, we can now study this opaque phase and unravel its mysteries. Enter the 21-centimeter line. This is a natural radio wave emitted by neutral hydrogen atoms. By detecting and analyzing this signal, astronomers can map the distribution of hydrogen in space and study the epoch of reionization. To accomplish this, several radio telescopes around the world have joined forces to form the Square Kilometer Array (SKA), one of the most ambitious radio astronomy projects ever undertaken. When fully operational, the SKA will consist of 197 dishes and 197,000 linear miles of receiver modules spread across 6 continents. Its primary goal is to detect the faint 21-centimeter signal from hydrogen gas, allowing us to peer into the hearts of galaxies and uncover the details of the epoch of reionization. But the SKA is not alone in this endeavor. Other radio telescopes, such as LOFAR in Europe and HEFA in South Africa, are also contributing valuable data to our understanding of reionization. Together, they are forming a global network of radio observatories dedicated to unraveling the mysteries of the early universe. However, the study of reionization is not limited to radio waves. Visible light offers another window into this era. In fact, some galaxies from the epoch of reionization have already been identified. For instance, GNZ 11 is one of the most distant galaxies ever discovered. Its light has been stretched by the expansion of the universe, shifting it into the infrared part of the spectrum.
I study.
Astronomers can gain insights into the conditions and processes present during the early stages of galaxy formation. To further explore the epoch of reionization, scientists are conducting a survey of bright Lyman break galaxies at high redshifts. These galaxies have a distinct Lyman break in their spectra, which occurs when the Lyman alpha emission line of hydrogen is shifted beyond the detectable range of visible light due to the expansion of the universe. By identifying and studying these galaxies, researchers hope to shed light on the mechanisms that drove reionization and galaxy formation in the early universe. So we have tools like gravitational lensing, spectroscopy, the Gunn-Peterson test, 21-centimeter line mapping, and surveys of Lyman break galaxies. These are just some of the methods astronomers are employing to study the cosmic dawn and epoch of reionization.
S.
As we conclude our journey through the dawn of our universe, remember that every step we take brings us closer to understanding our place in the grand scheme of existence. We are literally witnessing the birth of our cosmic home. With each new discovery, we peel back another layer of the universe's history, revealing the intricate processes that led to the world we know today. The quest to understand the universe has always been a testament to human curiosity and ingenuity. And as we stand on the threshold of a new era of exploration, we can marvel at the incredible tools we have created to unlock the secrets of the cosmos. From the James Webb Space Telescope peering into the depths of space to the Square Kilometer Array, listening. For the whispers of the early universe, these instruments are pushing the boundaries of our knowledge, allowing us to explore realms once thought impossible to observe directly. As we continue to probe the mysteries of the cosmic dawn and epoch of reionization, we can expect more surprises and revelations. Who knows what other wonders await us in the vast expanse of space? Perhaps we'll uncover evidence of the first stars, witness the birth of the first galaxies, or even discover new phenomena that challenge our current understanding of the universe. The journey through the cosmic dawn and epoch of reionization is not just a scientific endeavor. It's a reminder of our place in the grand tapestry of existence. It shows us that we, as humans, have the ability to understand and explore the most complex phenomena in the universe. So let us continue to ask questions, to explore, and to push the boundaries of what is possible. For in doing so, we not only expand our knowledge, but also our appreciation for the beauty and complexity of the world around us. Before the dawn of time, before the first stars flickered to life, before the cosmic tapestry began to weave itself together, the universe was engulfed in an impenetrable darkness. A sea of particles stretched endlessly, silent and empty, broken only by the faint whispers of the cosmic microwave background. This was the era of the cosmos' dark ages, period so shrouded in mystery that even light itself seemed imprisoned within an invisible cage. But then, something extraordinary happened. A cataclysmic event that would echo throughout eternity, an event that gave birth to the universe as we know it. It was a transition so profound that astronomers have given it a name, reionization. Reionization, however, is more than just a chapter in the cosmic story. It is a testament to humanity's unquenchable thirst for knowledge. As we stand on the threshold of unraveling its secrets, the future beckons with exciting possibilities that promise to not only illuminate the past, but also reshape our understanding of the cosmos, symphony of light. At its core, reionization refers to the dramatic shift in the state of the universe. In the aftermath of the Big Bang, the cosmos was filled with a primordial soup of particles, a sea of protons and neutrons adrift in a quantum foam. As the universe expanded and cooled, these particles began to coalesce, forming the familiar hydrogen atoms. For a brief moment, the universe was bathed in a soft glow. As electrons spiraled around their atomic cores, they emitted a faint light. But this era of tranquility soon came to an end. The free electrons, those not bound to atoms, scattered and absorbed the light. Photons bounced off them, trapped in an opaque fog that muffled the universe's first feeble attempts at illumination. This period, known as the Dark Ages, lasted for hundreds of millions of years. Then the first luminous objects ignited, perhaps gigantic gas clouds collapsing into massive stars. These stars blazed with otherworldly brilliance, spewing an intense radiation that tore apart the surrounding hydrogen atoms. Electrons once again found themselves unbound, streaming outward from the nuclei and creating a sea of plasma. This ionization process transformed the universe. The fog lifted, and light poured through the cosmos unimpeded. Stars twinkled, galaxies shimmered. The universe was no longer a silent void. It was a symphony of light. Cracking the code, understanding the nature of this cosmic transformation is crucial, because it holds the key to understanding how the universe evolved from a chaotic primordial state into the structured world we see today. It helps scientists learn about the conditions under which the first luminous objects ignited, whether stars or black holes. And it allows researchers to examine how matter coalesced into the first galaxies, shedding light on the very essence of cosmic creation. By peering deep into space, astronomers see not only distant galaxies, but also glimpses of the universe's youth. They seek out the faint signals of the earliest luminous objects, hoping to catch a glimpse of the universe's awakening. Studying reionization also gives us insights into the emergence of heavy elements, those forged in the furnaces of stars and scattered into the cosmos upon their deaths. These elements, including oxygen, carbon, and iron, became the building blocks for planets, moons, and ultimately life itself. By understanding how and when these elements dispersed, we gain a deeper appreciation for the rarity and preciousness of life. In the years ahead, several ambitious projects are poised to make groundbreaking contributions to our understanding of reionization. Foremost among them is the Square Kilometre Array, an ambitious radio telescope currently under construction in South Africa and Australia. With a collecting area of 197 dishes spread across 2 continents, SKA will conduct the most sensitive radio survey of the sky ever undertaken. When operational, it will directly map the 21-centimeter signal of neutral hydrogen during reionization, producing the first 3D movies of how the fog of the early universe was cleared away. Additionally, high-resolution quasar surveys will scrutinize the last pockets of neutral hydrogen, giving us tighter constraints on the timeline of reionization. On the theoretical front, researchers are developing sophisticated computer simulations that model the universe's evolution. From the Dark Ages to the present day, these simulations incorporate the latest data on the cosmic microwave background and galaxy formation, allowing scientists to test various hypotheses about reionization and refine their understanding of the universe's early years. Moreover, theoretical work is focused on refining models of the first luminous objects, including population 3 stars and their potential black hole seeds. By studying the properties and life cycles of these celestial bodies, researchers are piecing together the intricate dance between matter and radiation that shaped the early cosmos. Finally, laboratory experiments are recreating the extreme conditions of the early universe to better understand the physical processes that occurred during reionization. These experiments use powerful lasers and particle accelerators to simulate the high temperatures and densities present in the primordial soup, shedding light on the fundamental physics that governed the universe's evolution, peering into the depths. In the coming years, these research efforts will converge, illuminating previously unseen aspects of reionization. Some of the most anticipated discoveries include the identification of the first luminous objects that sparked the ionization process. Whether these objects were massive stars or black holes, their discovery will provide invaluable insights into the nature of the universe's birth throes. Another anticipated breakthrough is the precise mapping of the distribution of matter and radiation during reionization. This will shed light on how the universe transitioned from a state of homogeneity to the formation of the first stars and galaxies. Perhaps most tantalizing is the prospect of discovering biosignatures, chemical or physical signs of life on planets that formed during reionization. While highly speculative, the possibility of finding ancient life forms could revolutionize our understanding of life in the universe. As we peer deeper into the cosmos, we are confronted not only by the immensity of space, but also by the immensity of time. Reionization serves as a reminder that the universe has existed for a period far beyond human comprehension. Our quest to understand it is a humbling experience, urging us to appreciate the vastness of the cosmos and our place within it. In the end, studying reionization is more than a scientific pursuit. It is a journey to the heart of the universe's evolution, a testament to the indomitable spirit of human curiosity. As we continue to explore the mysteries of the cosmos, reionization stands as a beacon, guiding us toward a deeper understanding of our origins and the boundless wonders that lie beyond. The discoveries that await us are nothing short of revolutionary. The dawn of the cosmic era, the birth of galaxies, the emergence of heavy elements, and the potential signs of early life all beckon. With the promise of reshaping our understanding of the universe, reionization is not just a chapter in the cosmic story. It is the foundation upon which the universe as we know it was built. It is a testament to the relentless march of progress that has carried us from the depths of darkness to the heights of enlightenment. And as we stand on the threshold of unraveling its secrets, we do so knowing that we are part of an enduring legacy of exploration and discovery that has defined humanity's journey through the ages.